I will also do that. Yeah. Okay. So I have Aij, this thing, plus the gammas, Christoffel symbols. So the way you do it is the following, that, no, I see. Okay, just a minute. Okay. So for the covariant derivative of a covariant vector, it is a minus sign. I have a gamma and I will have a A. Now, this is AI, so I will replace it by some dummy index AA, which will be contracted with A. There is a derivative J which will go here. And the I of this will go here. And in the case of contravariant, I will have AI semicolon J is equal to AI partial derivative J plus gamma A. Now, this AI is there. Now, this will be A. And if to contract this, I will have an A here. The I will go here from this I and the J will be for the derivative. Is it okay?
Yes.
Harish?
Yes, yes.
Okay. And we also saw that if we have a contravariant vector, Tik, Tij semicolon k, this is equal to Tij comma k plus gamma t plus gamma t, because there are two covariant, there are two indices. Now I will choose them one by one. Let me just replace the I one. So the J is as it is here. The derivative K will appear here. And this J has to be, what did he do? Huh. And the I which is there will be replaced by A, and doing some goof up, just a minute. Okay. So I have Tij semicolon K is equal to Tij comma K plus gamma T plus gamma T. Now in the first one, I will replace I. So I will leave J as it is. In the second one, I'll replace J. So I will leave I as it is. Now, whatever I have not replaced, I will put it as A, which has to be contracted with A. I will put it as A, which has to be contracted with A. Now, here, this is a J here. So the other I index comes here, is a I here. So J index comes here. And this is the derivative. Are you okay with this?
Yes.
Okay. It's just practice, it will come, like, so now, and if suppose I have Tij semicolon K, this will be Tij comma K. Now there is one contravariant. So I will have a plus gamma T, and the other is covariant. So I will have a minus gamma T. When I'm replacing the contravariant, this I has to be replaced. So I will put an A, which has to be contracted with an A here. The derivative K will come here. And the extra index I will come here. In the other case where it is covariant, the I will be as it is. Oh, there is a J here, sorry. The I will be as it is. J will be replaced, say, by B, which will be contracted with B. the derivative will have a k, and there is one extra index j which will come here. All right?
Yes.
Okay. So this was what we saw. Now let us see one very interesting property of gammas. Okay. And this is where we will now start using extensively the fact that you prove a tensor relation in flat space-time. Since it's a tensor relation, it is not only valid in flat space-time, but any space-time. So I go to the any space-time, and I'll just show you how. Let us consider a scalar field, phi. Okay. Now the derivative of the scalar field is phi comma I. The derivative of a scalar field is a tensor, right? We already saw that. It's a covariant vector. So it's a tensor of single rank.
Yeah.
Let's just call it as, okay, so I will call this vector, just for convenience, as AI. Are you with me?
Yes.
Yeah.
Okay. What I will now do is, since it's a vector, now to take derivative, I have to use covariant derivative. So I will have the covariant derivative of A with respect to J, AI semicolon J, will be equal to AI comma J minus gamma A, the J derivative which comes here, and the other index comes here. All right? Okay?
Yes. Yeah.
Now I will rewrite this equation in this way, that AJ semicolon I is equal to AJ comma I minus gamma A. Now it will be JI. All right?
Yeah.
And now I will subtract these two. So I will have AI semicolon J minus AJ semicolon I is equal to AI comma J minus AJ comma I. Okay. Plus plus gamma AJI minus gamma AIJ, the whole thing into AA. Are you with me?
Yes.
Yes.
And now what is this? This is AI semicolon J minus AJ semicolon I, and I now use this definition here. This is equal to phi comma I comma J minus phi comma J comma I. Okay?
Yes.
Okay. Plus gamma AJI minus gamma AIJ AA. This quantity is del 2 phi by del xi, del xj, del xi minus del 2 phi del xi del xj, which is equal to 0, because order of partial derivative does not matter.
Yeah.
Okay. And so I have AI semicolon J minus AJ semicolon I is equal to gamma A JI minus gamma A ij AA. This is a vector. This is a tensor. And hence, by quotient law, this has to be a tensor. So you see something very interesting. Gamma Aij is not a tensor. But if you reverse the lower indices and subtract, the difference is a tensor. So the tensorial, the non-tensorial nature gets cancelled out. Okay?
Yeah.
Okay, fine. So now, so I have gamma Aij is a tensor. Now, in Minkowski,
And says the last result that you proved,
huh,
I guess it can be proven for any particular contravariant vector, right? Like not specific to gradient of a scalar.
no, I will tell you why I wanted it. Because I wanted this interchange of these two indices over here.
Yeah,
I'm
but the
sure it can be.
non-tensorial part cancels either way, right? Like it doesn't depend on.
No. Otherwise, suppose it was a general vector. I will have ai comma j minus aj comma I. If ai is not a partial derivative of a scalar, I can't cancel this out. Right? You understand?
Oh, yeah, got it. Yeah, got it. Like I was just looking at the transformation of that Christoffel symbol and then confused with this.
Yeah. But this is why I just took this thing to do it.
Okay,
This is very best thing this way.
got it,
Okay.
got it.
Now, in Minkowski, we know that covariant derivative is equal to partial derivative. Why? Because the difference between them is purely because of the coordinate artifact, because the the coordinate system is not rectilinear. Once you have a rectilinear system, there is no extra coordinate artifact when you take the derivative of a scalar, of a vector, right? I mentioned to you why in special relativity you don't have to find this difference. You have to use this difference. Remember?
Yeah.
Yeah.
Okay. It means that gammas in Minkowski equal to 0. Because gamma is the one which takes into account change which is not physical but because of coordinate artifact. Right?
Yes.
Yes.
Okay. Which means gamma Aji equal to 0 and gamma Aij equal to 0 in Minkowski. But here you can't say much after this because my gammas are not tensors, so I can't generalize it. You get the point? See, if I go to another coordinate system, this gamma will change. It's not a tensor.
Yes.
Right?
Yeah.
Okay. But now
So,
let me take the difference.
Sesh,
Yeah.
when we have
Yeah.
an equation, like let's say we have a tensor plus this connection term, right? It is not a tensor.
Yes.
So, I mean, can we have an equation like that? Because on the LHS we have a tensor sum. And on the right hand side we have tensor plus something that's not a
No. We
tensor.
can't have it. We can never have it. Where is it?
The connection term.
No. In connection term, which one? This term here.
Ah.
Yeah, but this is not a tensor, no? Partial derivative.
Okay.
Okay. So it is a non-tensor nature of partial derivative, and the non-tensor nature of the second term cancels each other to make this left-hand side a tensor.
Okay.
Fine. So now I take the difference. Now I calculate the difference. It is gamma ji minus gamma aij is also equal to 0 from these two.
Yeah.
Right?
Yes.
But now you see the interesting thing. This difference is a tensor. Okay?
Yes.
In Minkowski. Now, since it's a tensor equation, it should be true for any coordinate system. LHS is a tensor. Hence, gamma aji minus gamma aij equal to 0 in any system. Now, what does this mean? It means gamma aij is equal to gamma aji in all systems. Implies gammas are symmetric. They are not tensors, but they are definitely symmetric in the lower two indices. You get the point?
Yes. Yes.
Harish?
Yes, got it.
Singha, you are, I think, I know you will be difficult to follow it, no?
Yeah, a little bit. It's
Okay. Okay, so I will share the recording and the notes. You just let me know, then we can discuss it later separately.
okay.
Okay, so I have this thing. Now let me get more greedy. Okay. Okay, let me get more greedy. Let us consider the covariant derivative of the metric tensor. Okay. And there is a certain reason why I am considering it. First of all, in Minkowski, system, Gij semicolon k is equal to Gij comma k, because gammas are 0.
Yeah.
But we also know that in Minkowski, Gij equal to eta ij is equal to constant. Which means that Gij comma k equal to 0 in Minkowski. All right?
Yes.
But since Gij comma k is same as Gij semicolon k in Minkowski, I mean, yeah, this is equal to 0 in Minkowski. All right? In Minkowski.
Yes.
Now, can you tell me something?
It is true in
For all correct.
It's true for all systems. So Gij semicolon k equal to true in any system. You know, I will not go into the details, but it is actually it is related in a very interesting way. It says that if I take any smooth surface and I take a point in that, I can always draw a tangent plane, which is a flat plane. That is what it says actually. I mean, forget it. I mean, because it's more confusing. I just wanted to mention.
Could you repeat?
See, basically, what it says is, if suppose I take a sphere or any smooth surface, which need not be flat. Okay?
Okay.
I can go to any point and construct a tangent plane, which is a two-dimensional plane and is tangential to that surface. It means I have constructed around that point a locally flat space.
Yeah.
Okay.
This is a space-time statement about it. I can always construct a locally flat space-time. This is like saying that since Gij, comma K is 0 in Minkowski in the locally flat space-time, I can always get it around that place in this form.
Okay.
Okay. So this is a very important thing. Okay. And now it gives me the weapon to calculate the explicit form of gamma. And I will do it in the following way. Okay. Deriving the functional form of gammas. I have Gij semicolon K. Let me write it in the usual definition of covariant derivative. Gij, comma K. Now both are covariant, so I will have a minus gamma G minus gamma G. I will take the, so first of all, K is the index for derivative, which will come with gamma. Now I will take these indices of Gij one by one. First, I will replace the I. So I will keep it as A and I will put it as A. And then this will be the remaining one J and the remaining thing I will come here. And in the next one, I'll keep the first one, that is the I where it is, and replace J by A. I'll put an A and then put a J. All right?
Yes.
Now I do the following. I rewrite the same equation by I replaced by J, J replaced by K, and K replaced by I. I can call them by any name. So I call them by a different name now. So I have, if I just cyclically rotate it, Ki semicolon J is equal to G Ki, comma J minus gamma G minus gamma G. So I was replaced by K. So it is K and K. Then J was replaced by I. So from the first equation I have, I'll put an I. And I will put an I. And K was replaced by J. So this K out here, I will replace it by J here. It's K by J. And then this I was, K is here, so it will be A, 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 A. Is that all right?
Yes.
Oh, what am I doing here? Sorry. And I'll do again the same cyclic rotation. I mean, I can actually take it directly from this definition. I need not go to the first one and then change it. Okay, we'll just do that. J, K, comma I equal to G, J, K, I mean, semicolon I, J, K, comma I minus gamma G minus gamma G. Okay, so I'll replace this by one. So the first one will be j, which I'll replace. I will put an a, and this will be j. The derivative is now I, and the other index is k. Similarly here, I will keep the first index same, which is j, replace the second index k by a, and okay, and then this derivative by I, and that leaves I, no, I have a mistake. I have done a mistake. Sorry. I have the derivative of I, which is here. I retain the first term, which is j. Okay. The k, something is wrong here. Wait. So I have gamma, which then I have g. Then I have a derivative is I. So I put the derivative I. I retain the first index. I retain j. The second index, I put it here. I see. I'm a bit puzzled by this. Wait a minute. I, oh, I'm stupid. Okay, fine. Let me do it again. So I have a derivative with respect to I. So I'll put an I here and an I here. I will first replace the first one of j. So I'll keep k here and put an a and an a. And the remaining thing is j, which goes here. Yeah, that's not k, but j. Similarly, over here, I will retain now the first one, which is j. Replace k by a, and I'll put a k here. All right?
Yes.
Yes.
Okay. But I know that this is equal to 0, this is equal to 0, and this is equal to 0. Just now I proved it. Okay?
Yeah.
Yeah.
Yes?
Yeah.
And so I can replace this entire thing by um, okay?
Yes.
Okay. And now what I will do is, this is equation 1, equation 2, equation 3, and I will do 2 plus 3 minus 1.
Wouldn't there be a plus sign there?
Pardon?
I think there should be a plus sign there, no?
Where?
In between the gammas.
Oh, I see. Yeah, of course. Because I'm changing sides. Yeah, okay.
Yeah.
Yeah, that's correct. Thanks. Okay, and so this will mean G K I, comma J plus G jk comma I minus G ij comma k is equal to, now let us consider these. So the first, this will be gamma A k j G a I and yeah. So just to, okay. I know, I'll just a minute. Okay, let me just write it in a particular color so that it'll be easy to understand. Okay, and so now I will put it this way that so because you can keep track of what term comes from where. This is okay. Oh no.
Kij is purple.
I'm just doing so when you are actually going back and looking at it, then it's easier for you to follow. Okay. This is equal to, now this will be this term, and then I will have plus gamma Aij Gka plus gamma Aji Gak plus gamma Aki Gja minus, okay, or, okay, just a minute. So I have enough space. Okay, minus this one, gamma Ik Gaj minus gamma Jk Gia. All right?
Yes.
Okay. Now I will use another, this one. Okay. This quantity and this quantity cancels because gamma and G are symmetric. Right?
Yeah.
Similarly, this quantity and this quantity will cancel. Again, gamma and G symmetric. Okay?
Yeah.
Right? And so this is interesting. Now that leaves me with Gki comma J plus g jk comma I minus g I j comma k is equal to twice gamma a I j g k a, again because gammas and g are symmetric. Because these two have the same plus sign. Okay, so this one I will put it as, what color shall I use? I will use this light green color.
Use white.
Pardon?
Use white.
White. It has all the colors.
Yeah.
So you get this?
Yeah.
Yes.
Yeah.
And now you play the trick. Now what you do is, you multiply both sides by g k b, upper contravariant. And so I will have gkb gki comma j plus gjk comma I minus gij comma k is equal to twice gamma a I j gka gkb. Right?
Yeah.
And what is this equal to? Twice
Delta.
gamma aij. This is
Delta.
basically gba, which is basically twice gamma ij delta function of ba. Because you see, gkb is inverse of gka. So their product should be identity, which means it is 1 in the diagonal term and 0 everywhere, which is this delta function. Is that okay?
Yeah.
Yes.
And so I have gkb gki comma j plus gjk comma I minus gij comma k is equal to twice gamma bij. And I will just take this half and I'll go here. I have now got a formal expression for gamma in terms of the metric tensor. Is it okay?
Yes.
Okay, so for the first time, now we have got this thing, which is important. Till now, we are telling a lot about the properties of gamma. Nowadays, in internet, you will have something like, this person opened the cover and he found something strange. Then you click. Then it says some story, then it's happened. Then it'll say some story, this happened. Then it'll say, and after some 30 slides, there'll be something trivial. So till now we have been talking about various things about gamma without telling what is gamma. Finally, now we have told what is gamma. But you required all these properties to get this. Okay?
Yeah.
So it means that now suppose I want to find the covariant derivative. Okay? So suppose I want to find the covariant derivative, say, of a scalar. Derivative of a vector. So suppose I have ai comma j. What do? I first of all find the gij's there and I get gij comma k's. I get gamma and then I write ai semicolon j is equal to ai comma j plus gamma I a j a. Right? So now we have a formal prescription for calculating things. Is it okay?
Yes.
Okay, so, I mean, should we stop here or should we continue?
If we continued, what will we discuss?
Okay, we will now start discussing the geodesic equation in free space.
Then we could continue.
Pardon?
Then we could continue.
Okay, so let me just do that. So now I will say geodesic equation, by which I mean the following. Trajectory of a free particle. By free, I mean free in the Einstein sense. If there is pure gravity, it is still free. It is just that the space-time is curved. Right?
Yeah.
Which I have been telling you. Okay? So gravity is not a force. Okay? Now let us see this. In Minkowski, is it Y or I, Minkowski?
I.
No? Yeah, my spellings are horrible. All these scientists, if they come alive, they will kill me because of the spellings I use. Okay. In Minkowski, dui is 0 for free particle. That is, the velocity does not change. Okay? All right?
Yeah.
Fine. It means that del ui by del xj dxj equal to 0. Now this is true for all dxj. It means del ui by del xj is equal to 0. All right?
Yes.
Yeah.
Now, this implies ui comma j equal to 0. Can you now guess what I will do?
Y semicolon j equal to 0.
Yes. So this implies in Minkowski, ui semicolon j equal to 0. This is a tensor equation. Hence, for any curved space-time, ui semicolon j is 0. Now, what? This is the interesting thing. It means that now, in the presence of gravity, this is my trajectory of a free particle. All right?
Yeah.
Okay. Yes. Now let us just play around with this. A bit. What does this mean? This means ui semicolon j is equal to 0 implies that ui colon j plus gamma I ua aj equal to 0. All right? Okay?
Yes.
Yes.
Now, I multiply by dxg. So, I have del ui by del xj dxj plus gamma iaj ua dxj equal to 0. Divide throughout.
By ds.
No, dx. Okay. So this, yeah, ds. So now, okay, no, this will be dui plus gamma iaj ua dxj equal to 0. Now divide throughout by ds. dui by ds, because it's a scalar. What is this object? dxj by ds?
Acceleration.
Pardon?
4 acceleration.
4?
4 acceleration. Wi.
No. It's 4 velocity.
No, the other. Okay. No, the other.
That's right. Okay.
Okay.
So this I can write as d2xi by ds square plus gamma j gamma I aj ua uj equal to 0. Is it okay?
Yeah.
Yes.
So it's something like the 4 acceleration, which in my Newtonian language should be 0. But here what is happening is, because of the curved space-time, it is getting modified. Okay. And if I now multiply by the mass, which, as I said, mass is only rest mass, this will be dpi by ds. This is the proper rate of change of momentum, plus gamma iaj ua pj equal to 0. Now, this is the geodesic equation. This or this is a geodesic equation for a particle in a pure gravitational field, in a curved space-time. I'll come to gravitational field later. Is that all right?
Yes.
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 Now, there is something very interesting you find. This means that d2xi by ds square is equal to minus gamma ij ua uj. Now, this is like Newton's law, right? In some sense, except for the time by proper time acceleration. And then if I have m, I will have this as pj. So it is something like this is the equivalent of the ith component of force. It's a generalization of the ith component of force. Something like that, okay?
Yes.
Okay, fine. And this will play a very important role. Now what we will do is the next step is consider a GMIJ, which is almost Minkowski, but slightly different from Minkowski. What I will do is, I will say that Gij is equal to eta ij plus hij, where hij is much less than 1. That is, I want to get the Newtonian limit. Okay?
Yes, yes.
And this is weak gravity. Further, in Newtonian equation, there is no time dependence, an action at a distance. So I will neglect all time dependencies. That is, since I take c to infinity, I will neglect all time scales so that there is no, so that, I mean, so if suppose c is infinity, then it means that signals get propagated at infinite speed. So there is no time, there is no time evolution. Okay, I will just elaborate on that. So now I'll take this thing, I'll take gamma IAJ. And if I look at my earlier expression, I will have 2G IB G B A comma J plus G B J comma A minus G A J comma B. This was the expression we derived. All right?
Yeah.
Okay. Now, correspond, okay. So this quantity, okay, so now GIB is equal to inverse of this. I think it is getting very heavy today, right? Okay, so let me just give you the result. I'll derive it next time. Basically, what will happen is, since Gij is equal to eta ij plus hij, and eta is a constant, these will just become hba comma j plus hbj comma a minus haj comma b. All right?
Yeah.
And here it will be half eta ib plus the upper hib. Okay? Now you find that if we retain only to first order in H, because I want to look for weak gravity. See, because I have experimental observations with Newtonian gravity. Now I want to see if I bring to Newtonian limit, what kind of a thing do we get? Do you understand?
Yes.
Yes.
So this up to first order, this into this will be second order. That is this, this, and this. So we'll neglect this. So we will just have half eta ib hba comma j plus hbj comma a minus haj comma b. Now I will suspend the summation sign and explicitly put the summation sign, which means that, okay, so this is gamma iaj equal to b. So it will be summation over b. All right? And now I go back to my original thing which I wanted to do. m d2xi by ds square is equal to minus gamma I aj u a. Okay, so let me just remove this m here. Okay.
Sis, can you explain the summation over B part again?
No. See, because here I find B is the only repeated index, na?
Okay.
Okay, so that is, so I'm just putting it explicitly.
Okay.
And here I will put it as summation A comma G.
And why are you not contracting it? Like you just keep it as B.
Which one?
Like eta IB, you can just contract it with other H tensors. Right?
No, there's a bit of, yeah, but then I don't know what is H upper B. So I want to convert into a number and then multiply.
Okay.
Okay. Now, what is it that is Newtonian acceleration? I will have I equal to alpha, which is 1, 2, 3, because I'm looking at only spatial sections. And ds goes to dt in Newtonian limit. So the left-hand side is d2x alpha by dt square. All right? The acceleration. And this is equal to, now I want I as only alpha. Okay?
Okay.
I want it as only alpha. So let me go to this thing. Now, eta IB is equal to, is what? Is diagonal 1, minus 1, minus 1, minus 1. Right?
Yeah.
It is Minkowski. But these are the ones which are related to space. So eta alpha B is equal to diagonal minus 1, minus 1, minus 1, which is basically minus of delta alpha B. Are you with me?
Yes.
Okay. And so I take this, and I write this as half summation over B with a minus sign, delta alpha B H B A comma J. No, it'll be very intricate. I'll take it next time, because the point is, I mean, it will be very long actually. I think. See, basically what I will have to do is, I will have to substitute for all this in terms of H. Then I will have to take the limit of small h and space independent. And basically, I will tell you what is the expression I will get. Then I will do it next time. Just a minute. I've got my notes here. I will basically get this whole thing as in this limit. I will get d2x alpha by dt square is equal to minus half del by del x alpha h00. Okay. You need not bother about this alpha being up and down, because I have suspended that thing. Explicitly, I'm using eta, so it doesn't matter. Are you with me?
Yes.
So
Yes.
what does this mean in the usual vector, three-dimensional vector notation? d2x by dt square is equal to minus half gradient of h00, right?
Yes.
But I know from Newtonian equations that this by this in the presence of gravity is minus gradient of the gravitational potential.
Potential.
So this means a very interesting thing. It means that h00 is just h00 by 2 is just phi plus some constant. The first time you have now got the connection between gravity and space. The h00, which is coming from space-time, has been related to the Newtonian gravitational potential. And so I have h00 is equal to 2 phi plus 2k, and g00 is equal to 1 plus h00 because eta 00 is 1. And so this is equal to 2 phi plus 2k plus 1. Okay?
Yeah.
Some small problem. h00 is equal to, gives. Okay. But I know that in the limit of zero gravity, phi goes to 0 and g00 goes to 1. So in this limit, I should have 1 is equal to 2k plus 1, which means k equal to 0. Are you with me?
Yeah.
Yeah.
Which means that h00 is equal to 2 phi and g00, my 00 component of metric tensor is nothing but 1 plus 2 phi. If you put we have taken c equal to 1, but if you put c, this will become by c square. The first time you have got the actual relationship between geometry and gravity now, by comparing with Newtonian thing. Is that all right?
Yes.
Yes.
Okay, so I will stop here. I just wanted to, because I've been talking about geometry. At some point, I want to tell you that, we have now gravity coming in, knocking at our doorstep. Okay.
Yes.
Yes. Okay. So I will continue next time.
All right. Sir, I want to ask you about the project I was asking you, like studying the primordial magnetic fields.
Oh, yeah. I have to send you that material.
Yeah.
Okay. No, but the point is, we need to get to some relativity and cosmology before we do that, no?
Yeah.
Because I'll be starting with, in that, the starting point will be the action for electromagnetic field in curved spacetime.
Okay.
Okay.
Okay. I've done that in the flat space time, but I think it will take